Now to continue our section, just to let you know and check if you are in the right room. We are in the track 10, applications of artificial intelligence to cybersecurity, okay? So now I'd like to invite Ahmed to present your work. Ahmed, welcome.
Well, thank you, and hello everyone. My name is Ahmed Alghamdi. I am a PhD student in computer science under the supervision of Dr. Giles Reger at the University of Manchester. In this presentation, I'm going to show our work on pattern extraction for behaviors of multi-stage threats via unsupervised machine learning algorithms. I'm trying to move to the next slide, but it doesn't work.
Robbie, could you help?
Perfect. So starting with the question, what are multi-stage threats and why they are difficult to be detected? Usually this type of threats or attacks is performed during a long period of time. And the attackers usually use zero-day vulnerabilities, encrypted codes, or some obfuscation techniques or social engineering to avoid being detected by intrusion detection systems. The graph on the screen shows an example of a simulated attack, multi-stage attack that was simulated in our virtual network at the university. As you can see, where the attackers start initiating the attack by collecting as much possible of data about the targeted individuals or organizations before actually initiating the attack. Once they manage to do this, then they can deliver the attack either by sending malicious codes like macrofiles or exploiting vulnerabilities on their targeted devices. Once they can manage to do this, then they can initiate command and control channel and apply lateral movements. That would include data exfiltration and privilege escalation as well. So during those multiple stages of the attack, there are a lot of abnormal or malicious behaviors that will be generated, and some of them will be recorded on the log files on the devices or the sensors, if we can call them. And examples of those log files will be system logs, security logs, application logs, network traffic logs as well. And examples of behaviors, abnormal behaviors that could be detected will be such as multiple failed logins to the computer or denied access to some resources on the computer. So there are a lot and huge information that exists in those log files that could be analyzed to extract meaningful information that could be provided to system administrators or users to more understand, to be more understanding the characteristics of the attacks and the abnormal behaviors on their computers. There are many solutions that were provided in this regards to analyze log files. Some of them will be signature-based detection systems, and other will be anomaly-based detection systems methods. And in recent years, the use of machine learning algorithms to analyze such files have been increased to provide meaningful information to system administrators. So logs of systems, applications, and networks can provide significant amount of information that can be analyzed using machine learning algorithms to determine abnormal or new patterns of behaviors. As I said before, like many solutions were provided by other researchers, those models either relies on supervised machine learning algorithms like support vector machines, which require enough labeled real-life training data, which is extremely difficult to be obtained for multi-stage threats like advanced persistent threats here. On the other hand, some other researchers use unsupervised machine learning algorithms, and some of those algorithms suffer from the high performance requirements, low accuracy rates, and the parameters adjustment method. So here in our paper, we propose an unsupervised framework that collects and analyzes heterogeneous log files to extract patterns and correlations of behaviors without the need of training data or previous knowledge of threats. For the evaluation of our framework, we use the Scan of the Month 34 dataset, which is a publicly available dataset that consists of heterogeneous log files that were collected from a honeynet that was targeted by several attacks, in which some of them have successfully managed to compromise the targeted device. However, this dataset is provided in its original format without pre-processing or labeling. Therefore, we had to produce our own version of the dataset. We used some technical reports that explain the characteristics of the attacks inside this dataset. Those technical reports were cross-validated and labels were extracted and used to label the events in our dataset here. The graph on the screen shows the time distribution of the events in the dataset. And as you can see, the range of time range of the data are 2 months of time that the data were collected in. And also you see that the types of files, log files inside this dataset have like multiple files like HTTP logs, IP tables, the firewalls, snort logs, system logs as well. Each one of these log files have different structure and features. So in our framework to extract the inner behaviors and their correlations from the collected heterogeneous log files, the framework is constructed by integrating 2 main phases of automated unsupervised data analysis along with an action center. The graph on the screen shows the main phases in our framework and the main components of those phases. So starting with phase 1, where we aim to investigate the inner behaviors inside the log files individually. So we basically collect the log files from the target device, our compromised device, and then we process them individually or in parallel to find the sub-behaviors or the patterns of behaviors inside those log files individually. We take all of those information that were generated from phase 1 and use them in phase 2 to find the cross correlations between events across all of the log files. For example, we wanted to know if some events that exist in the HTTP logs are related to some abnormal behaviors that were detected by intrusion detection systems, for example. And thus we can build the patterns of those behaviors. Lastly, information generated from phase 1 and 2 will be sent to the action center where the system administrator or the user in general can access them and generate notifications, alerts, charts, and reports. Each one of those phases will be explained in details in next slides. So in phase 1, the goal of this phase is to identify sets of behaviors inside each imported log file using an unsupervised clustering method. This phase consists of 4 main steps that were performed automatically by our framework. The first step is the data pre-processing, where the framework converts the events in the dataset from their original format, TXT, into numerical data. In the second step, where the framework automatically calculates the required parameter for our clustering algorithm. And then in the third step, the data clustering, where our framework automatically applies the data clustering and extract the predicted labels which represent the sub-behaviors of the log files. Lastly, which is the data enrichments, where we use the predicted labels and information extracted from the clustering step to tag the events in the log files. So speaking more about the data pre-processing step in our framework, where the framework automatically convert the imported log files into data frames, with feature sets and deal with missing values. During our experiments, we found that the non-categorical data in our dataset here can be classified or grouped into three main data types. The first one is the ordinal categorical data, which are values that have logical order or scale between them, like priority levels from 1 to 3, for example. And the second type is the nominal categorical data, which are descriptive values with no connections between them, like names of devices or usernames, for example. The last type of the data, the non-numerical data we found in the data set, is the text data, which is basically a mix of data like web links, directories, and symbols. The graph on the screen could summarize the main automated steps that are performed by our framework to convert the non-numerical data in the data set into numbers. The first one starting with the ordinal categorical data, where the framework basically converts the unique values in the columns into numbers using, for example, a label encoder in scikit-learn. In the second type, the nominal categorical data, the framework creates dummies or new column for each unique value in the original data set or data frame here. Lastly, for the text data, the framework uses regular expressions to split the texts and then tokenize the unique values, and lastly combine the converted strings into numbers. From our experiments, we found that this approach of converting the non-numerical data into numbers that could be processed by our clustering algorithm is more practical and robust. And it also shows this accurate distances or differences between the events, rather than using one method or default method that exists in many machine learning algorithms or machine learning platforms like Reger or scikit-learn. So for the clustering algorithm here in our framework, we tested many unsupervised machine learning algorithms, such as k-means, DB-scan clustering, and EM, to evaluate the purpose, to find the most suitable one in terms of speed, robustness, and the parameters tuning. DB-scan was selected for our framework due to its ability to handle outliers and the identification of clusters without prior knowledge of the actual number of clusters. Basically, DB-scan is a density-based clustering algorithm that relies on two main parameters, which is the minimum points required to form a cluster. And the second parameter is the epsilon value, which is the maximum distance between two examples for them to be considered in the same cluster. The graph on the screen shows an example of clustering some data using DB-scan clustering algorithm. As you can see, like two clusters were generated from our data here, and two data points were grouped and classified as outliers because they didn't meet the criteria of the parameters. So those parameters that we talked about are calculated automatically by our framework. The framework automatically calculates the epsilon parameter and finding the optimal value of this parameter by finding the distances between all data points, and then calculate the mean of the unique slopes between those distances. Finally, the calculated mean is used as a value for the epsilon parameter. And in regard to the minimum points parameter, it is selected based on the processing methodology of our framework. On the right side of the slide, you can see an example of a generated chart from our framework, where the framework calculated the optimal epsilon value for the file HTTP access log. The same process will be applied in our framework for each log file as well, and a chart will be generated similar to this chart showing on the screen. So in phase 2, where we aim to correlate behaviors based on a set of common features that exist in log files, those common features will be like dates, times, process ID numbers, and other features that exist in most log files that will help us to find similarities between events in those log files. The following points explain the main components of this analysis phase, which is the patterns extraction. The first one is the cross-correlation log, where the framework automatically combined the processed events from phase one using common features. The main point behind doing this and combining all of the events in this log is to find the cross correlations among all of the log files and what similarities are linking and can be found in those log files. In the next step, the framework converts all of the dates and times into Unix format. From our experiments, we found that this format of time and dates represent more accurate distances between events more than using the default format. It is also compatible with our clustering algorithm as well. Lastly, in this step, the parameter calculation and the clustering algorithm is applied on the cross-correlation log the same way as applied in phase one. In the second step, which is the signatures extraction, descriptive signatures are generated for all resulting clusters from step one, which is the cross-correlation log. A signature for a pattern will consist of frequency rate, involved IP addresses, inner behavior rate tags, start and end date times, Avogadro forwards, file names, ports, and the status codes. Lastly, we combine all of the descriptive signatures that were extracted from this step into a correlated event record. This record is a persistent record of extracted signatures from all time series, which means that if our framework would apply further analysis on new log files, then the extracted signatures from those log files will be also inserted into this record. This will allow the system administrator through the Action Center to identify new behaviors and repeated behaviors as well. Also, the Action Center can be managed by the system administrator to access this record to generate notifications, alerts, charts, and reports. For the results of our framework, starting with phase one, where the results revealed that the applied methodology can process high numbers of events in short times. For example, in Sonort log file, which contains over 69,000 events, it was processed in less than 10 seconds. Also, the results shows that the framework has grouped events successfully with high accuracy rates due to the followed approach of data pre-processing and clustering. The tables on the screen summarize the results of phase one in our framework. As you can see, the times required for pre-processing and for the epsilon parameter calculation and the dbScan clustering algorithm are extremely low when we performed our framework on those log files. Also, we used other metrics like homogeneity, completeness, vMeasure, ARI, AMI to evaluate the performance of our framework. We found that the framework provides extremely high accuracy rates due to the followed approach of pre-processing and clustering. Regarding some files like HTTP SSL log, syslog messages, and secure, we can see the homogeneity of those files are 100% of accuracy because those files contain relatively small numbers compared to other files. Also, they include less complicated data that can be easily separated by our framework or by any other machine learning algorithm as well. For phase two in our framework, where we aim to combine or find the similarities of behaviors among all of the log files and the analyzed log files, we found that the pre-processing of cross-correlation log, which contains over 80,000 events, was applied in 1.9 seconds, while the clustering function was applied in 3.8 seconds. A total of 3,009 clusters were generated from the clustering process. Those clusters represent patterns of behaviors from over 2 months of recorded events. We wanted to more investigate those patterns, generated patterns from our framework. Thus, we used pairs of source and destination IP addresses to evaluate the homogeneity of the resulting clusters. We found that about 72% of the clusters contain unique pairs of IP addresses. In contrast, the rest of the clusters contain overlapping sessions, which indicate similarities between those sessions in times or in types of behaviors. On the right side of the slide here, you can see an example of an extracted pattern from our framework. As you can see here, there's like 3 different IP addresses performing exactly the same type of the attack and the malicious behavior. Although there's like a time gap between those attacks, which is like 5 minutes, and there are different ports that were used to initiate the attacks. All of those 3 attacks were combined into one pattern, and that shows the effectiveness of using our framework to analyze such files. So to sum up, our results demonstrate that the framework can efficiently cluster inner behaviors of log files with high accuracy rates and extract patterns of malicious behaviors and correlations between those patterns from real-world data. Currently, we are working on applying patterns recognition techniques on the collected data to allow some further analysis of the malicious behaviors. This will allow users to better understand relations between threats, and thus will allow the system administrators to build more effective methods of defense. Lastly, we are making the source code of our framework and the labeled version of the dataset available for other researchers for free. So if you are interested to learn more about our approach of pre-processing the data or the tools that we used to construct the framework, then you may visit our GitHub repository where you can find the full documentation of the framework and the dataset. If you have any further questions, then you may email me on my contact details that are shown on the screen. Thank you for listening, and now I will leave some time for the questions.
Thank you, Ahmed. Does anyone would like to make a question? I was going to ask you about the dataset because you said that there is one public dataset, but you decided to create a new one. Why did you decide to create a new one? And I was going to ask you if it's available, but you just said that it's available in GitHub. But why did you decide to create a new data set?
Actually, it is exactly the same data set. It's like the scan of the month. But okay, the data set available online, the scan of the month, is not pre-processed or labeled. So the work that we did is include labeling the data and pre-processing it and making it available for other researchers.
So that's much better. Thanks for the contribution.
Thank you.
If no one has question, I would like to thank you, Ahmed, and congratulations for your work. Good luck.
Thank you very much.
Thanks again. The next presentation is about 5 minutes. See you soon, guys.
Thank you.